Okay, here we go with our video on the definite integral. So I'm making this video right after I finished making this video about how you find the area of some amorphous region. And the way we talked about that was with inscribing rectangles. And then we built that up into this topic of what a Riemann sum was. And I tried to provide illustrations to go along with all the math and so on and so forth. And this is a continuation of that, all right? What I'm afraid of is that you won't really see how this is a continuation of that because the big picture is complicated. I guess if you wanted to focus on any one problem or any particular detail, it might not be that hard to understand. But if you try to think about all of this at once and see how it's interconnected, that will be a little bit harder, or maybe even a lot harder, okay? So you might not see how, even though maybe nothing in this video is particularly difficult, you might not see how it's connected to the last one, or connected to the one that I make after this, all right? Anyway, so let's start with some terminology. There's something called the definite integral. Here's our notation for it, okay? We read this as the definite integral of the function f of x over the interval a to b. We call a and b the limits of integration, okay? All right, so that's what the definite integral is. Now, just like anything, I mean, there is a way that you calculate this. There's a way that you do it. Maybe you can imagine all the way back to grade school where somebody says, this is called division right here. You see that symbol? That's division. And then they go about explaining what division is after that. So the first thing is just to say, here's the symbol, and we call it division, and here's how it works. You take 20 of something, divide it into 4 equal groups, and there's 5 in each group, right? That's what division is. So here, there's the notation. It's called the definite integral. And I have some other details included also. Okay, so what is it? What is the definite integral? There's a complicated answer and there's a simple answer. For now, I'll just say the complex answer has to deal with Riemann sums, and say you took the width of the widest rectangle in the partition of the Riemann sum and say you pushed that to 0, what would that entire calculation be as a limit? That's one definition. Now that one's hard to understand, I think. So let's not worry about the complex answer. I'll give you a simpler answer that you can focus on for now. What the definite integral is would depend on the nature of this function. Say that function was above the x-axis from a to b, a and b the limits of integration. The definite integral is the same thing as this area right here, the area contained by the curve and the x-axis from a to b. All right. But if that curve was below the x-axis, the definite integral would take a slightly different meaning. The definite integral from a to b of f of x dx is the negative or the opposite of this area. This area here being the area contained by the curve and the x-axis from a to b. So that's a simple answer to what the definite integral is. It's not really any different than this one, dealing with the limit as the norm of the partition goes to 0 of the, it's not really any different than that, but it's probably easier to understand. So let's work with this a little bit just so that we can get a little practice in doing the calculations and understanding the notation and so on. Okay? All right, so let's first problem. Evaluate the definite integral. Now, there are, it turns out, several ways you can do this. I have a disclaimer. The way I'm about to show you is not the only way. But, we have to learn something. And I can't show you 3 different ways to do a problem at once because, 1, that would probably be more confusing than it needs to be, and 2, it's just not practical. So I want to focus on this. We'll focus on these interpretations that I showed you right here. Okay? So evaluate the definite integral. All right, so Well, there's this curve, and there are my limits of integration. So let's just see what that looks like, okay? Since after all, I told you how you could interpret this in terms of area, all right, on a graph, understood in a very specific way. So I'll do a quick sketch. So let's see, there's 2, right? 3, 4, here's 5, all right. And I got -1, -2, 1, 2, 3, 4, 5. Okay, so that should be good. I notice if I just do a quick sketch that this curve, so to speak, hits the x-axis at 2. And then at 5, we're going to go up to 3 right there, right? 5 minus 2 is 3. And then at -2, I'm going to get, so -2 minus 2 is -4, but the absolute value is 4. So I get something like this. Here's the entire curve. Okay, so right there, that's y is equal to absolute x minus 2. Okay, now, how should we think about this? Right? Do you remember this thing I just told you about how to think about what the definite integral means? The definite integral means or is equal to this area right here. Okay? All right. So, in other words, what this is calling for in terms of a calculation is the area contained by this curve and the x-axis from -2 to 5. Well, that would be all of this, okay? There's the area contained by this curve and the x-axis from -2 to 5, all right? The limits of integration are along the x-axis. The curve's up there. I've shaded the area that is contained by all of that, and this is asking me for that total area. Okay, so, well, here's what I'd recognize about it. Okay, so that's a triangle. And how wide is that triangle? It's width of 3. And then how tall is that triangle? Where was this point again? That point was at 3. Okay, so that's that one. What about this one? Here's a triangle here, right? What's the width of that? So that's at 2, that's at -2. So width is 4. And then how tall is it? Where was this point again? Let's see, 1, 2, 3, 4. Okay, put -2 in, you get 4. So here goes. The grand total area contained by that curve and the x-axis from -2 to 5 along the x-axis is, for this first triangle, well, the area of a triangle is 1/2 base times height, right? That is how you find the area of a triangle. Since this graph does in fact make a triangle right there, and that's how I'm looking at it. So 1/2 base times height, okay. And then this other one, to take care of the rest of it, is 3 by 3. So 1/2 3 times 3 is again 1/2 base times height. So I'm seeing that whole area in terms of shapes that I'm familiar with. I'm seeing the area in terms of the generic meaning, in terms of something that I recognize, such as a triangle. So there, that would measure the total area contained by that graph from -2 to 5 along the x-axis. So this is going to be 16/2 plus 9/2, which is going to be 25/2. So there's your answer. The definite integral of the absolute value of x minus 2 from -2 to 5 is 25/2. Okay? Now, all right, so you might say, well, did we use the dx for something? And it's like, no, I mean, we don't really use the dx. It's part of the symbol, okay? It's part of the notation. We don't use the curly line right there either, all right? So we just got to recognize the total notation when you see it. Okay. All right, so one down. Now let's say we've got it's been established how you work these. Let's practice some others. And like anything I do, if you watch the videos, is you could pause this and maybe you could work that one out from what I showed you in the previous problem. You could try it, but I'll show you right here. So let's see. What are we looking at here? The definite integral from -3 to -2 of 2 minus absolute x dx. So let's take a close look at that. Since I'm doing this by thinking about it in terms of area, I will draw a graph. And as I said in this problem, what I'm about to show you is not the only way to do it, all right? But it's a way to do it that's consistent with what I'm trying to show you right now, okay? All right, so let's see. All right, so I got the x-axis, I got the y-axis. So let's see, 1, 2. Okay, so when x is 0, y is 2, so I got this point. And when x is negative 2, y is 0. And when x is negative 3, y is negative 1. So I'll get something like this. Okay, I got a few points on there, but it's going to look like this. And it's going to look like that. There it is. There's my curve. Y is equal to 2 minus absolute value of x. All right. Now, what are we asking for here? Or what's a way that you could interpret this? The definite integral from negative 3, which is here, to negative 2. Well, the curve is under the x-axis from negative 3 to negative 2. So we're looking for this area. Well, actually, in this case, the meaning of the definite integral is the opposite of that area. Okay, so look. Tell me how big this is. What's the area of that little triangle that's covered by my equation and my bounds of integration? Okay, or the limits of integration. Well, that's a triangle, and given that that point's at negative 2, but this edge was at negative 3, then that part of it, that's 1. It has a width of 1. And down here, where was this point again? Right there. That had a y coordinate of negative 1. So the height is also 1. So that's a 1 by 1 triangle. So the area of that piece right there that's covered by those limits of integration and so on is 1/2, right? Because it's 1/2 base times height. That's a 1 by 1 triangle. The area of such a triangle is 1/2 of a square unit, okay? All right. Now, in this case, though, we said that the meaning of the definite integral was it would be the opposite of the area. In the case where the curve is above the x-axis from a to b, the integral is the area so contained. In the case where the curve is under the x-axis from a to b, the integral is the opposite of the area that's contained. So it would be negative 1/2. All right, negative 1/2. Okay, so that's both interpretations then. 2 questions, both interpretations. Let's just see some things that are random, all right? Just kind of mixed up then. All right, what could this one be? Evaluate the definite integral from 0 to 4 of root 16 minus x squared dx. Okay, so first of all, a little bit about this. Hold on, let me draw a quick sketch. All right, so I got that sketch to magically appear. A curve of that form is actually a semicircle. Okay, so there's a lot to know in math, but you know, somewhere along the way, then you encounter graphs of familiar shapes like circles, and this is a semicircle. Okay, so I won't go into the whole explanation of that, but it's something that I could do if you needed me to. So I recognize that's a semicircle, and it seems from what I told you here that this number determines the radius. Like if that's a squared, then this edge is a and that edge is negative a, and the radius is a. So it's like when I look at this, I see, oh, 16, that's 4 squared. So this would be a semicircle radius 4. All right, so let's have a look at that. All right, and there's the graph of root 16 minus x squared. All right, so there we go. Y is equal to root 16 minus x squared. Okay, so now that just happens to be the graph of this. All right, now can you look at that try to figure that out with the graph, without the graph? It's like, sure, you can try to figure it out without the graph, but I'm trying to show you something very specific about how you can think of this. How can you think of this? Well, the definite integral from 0 to 4 of root 16 minus x squared dx can be seen as the area contained by that curve and the x-axis from 0 to 4. Okay, so it's going to be this. Okay, it's going to be that. The answer to this is the area of this region right here. Okay, that's the answer to this. If you can find some way to tell me the area of that piece, that's your answer to this definite integral. All right, so can you find some way to tell me the area of that? Well, this is a semicircle, and that would be half of it, so it's a quarter circle. All right, so let's say, all right, what I got here is a quarter of a circle. Let's see, what it's radius of 4. What's the area of an entire circle that has a radius of 4? Well, the area of an entire circle that has a radius of 4 is going to be pi times 4 squared. Okay, pi r squared. But this is a fourth of a circle that has a radius of 4. It's a quarter circle. So I want 1/4 of that. So what I got here is 1/4 of the area of like what would be like an entire circle that has that radius. Okay, so I just kind of imagine faintly there's this whole circle. Its area is pi times 4 squared, but that piece right there that's going to be my answer to this is pi times 4 squared over 4. So that's going to be 4 pi. All right, 4 pi. Because that is 16 pi over 4, which is 4 pi. All right, so not so bad. I mean, but you have to recognize you have to be able to do some basic things like sketch graphs and so on, okay? Like I have been able to draw the graphs of these, and that's helped me along as I've done this. All right, so we got that one. Let's try this one then, okay? All right, so definite integral from 0 to 9 of absolute 2x minus 9 dx. Now, how you draw the graph or how you sketch it or how you think about it, that's up to you. But just right now, I can, I'm familiar with what basic graphs look like and so on. And it's not that hard for me to do because I'm familiar with it. Maybe you are too, but let's say that if it really comes down to it, we can just plot points, all right? I mean, we could just do that if we needed to. Like, for example, if I plot some points, they're going to kind of form into this V pattern. And I know that the absolute value graph is going to be some kind of a V shape. It might be nice to know where does it hit the x-axis, all right? On some of the others, like this one, I thought it was fairly simple to say x minus 2. Well, if you put 2 for x, you'll get 0 for y. That's where it's going to hit the x-axis. This one will be kind of like that. Like, what if you set 2x minus 9 to 0? You'll get 9 over 2. Okay? So it's going to hit the x-axis at 9 over 2. 2 times 9 over 2 is 9, minus 9 is 0. That's its x-intercept. Other than that, if I'm looking from 0 to 9... it'll be something like this. What are you going to get in there when you put 0 for x? You're going to get 9 for y. Okay, and this is not to scale. Very rarely am I going to do a graph perfectly to scale, but it will work nonetheless. So I get 9 there, 0 for x, 9 for y. What about this one? What if we go to that outer edge right there? 9, okay, so 18, that's also 9. All right, so that's 9 times, or 9 for x, 9 for y. Whoops, 9 for x, 9 for y. Okay, so what's this integral represent? The area contained by that graph from 0 to 9. The area contained by this graph and the x-axis from 0 to 9. Well, so there's the whole graph, but I guess we're just looking at this part of it, like 0 to 9. Okay, so that, something like that. Yeah, so 0 to 9, there's the curve. There's y is equal to 2x minus 9, absolute value. Sure, that's it. If you can tell me then the total area contained in the shaded region, that's the answer to this, right? That's the interpretation I gave you when the video started about what this means. So let's see. This is, what's this right here? That's a triangle, right? What's the width? 9 over 2, right? That's how wide it is, from 0 to 9 over 2. And then how tall is it? Let's see, where's this point? How far up is that point? 9? Okay, so 9. All right. And what about this one over here? All right, how tall is it? Oh, also 9. Where's this point? 9. And then what's the width? Well, what's 9 minus 9 over 2? That happens to also be 9 over 2. So these are the same size. Okay, so let's do this. The shaded area is, let's see, 2 times 1/2 base times height. Okay, do you see what I did? The area of either one of these is 1/2 base times height, which is for either one, 1/2 times 9 over 2 times 9. But there's 2 of them, so I doubled it. So what are you going to get? 81 over 2. That's the total area. 81 over 2 square units of area. All right. Okay, that's what the math's going to be. And I could have added them together instead of multiplied by 2, but that's the grand total. So, okay, what's this one? The answer to this definite integral is 81 over 2, and we got it. Okay, so let's do one more example and then a little bit of interpretation of everything. So here's one where we read it again, the definite integral from 0 to 4 of f of x dx, but this function is more complicated than the others in that it's a piecewise function, okay? The meaning shouldn't change. I'll keep going back. I keep repeating how I'm doing this so that it sinks in. That you've got a function. You've got your limits of integration. Either way, we can interpret it in terms of area, all right? Just depends on if the curve is above the x-axis from A to B or below it from A to B, okay? All right, so there you can do that. This one would fit into that, but let's look at this. All right, what does that function or what does that curve look like? If you look at it from 0 to 4, what are you going to see and how are you going to think about it? Okay? All right, so here goes. It shouldn't be that hard to graph because I'm just talking about y being 5 continuously if x is less than 1. So just imagine like you got 1 there and you got this right here and it goes that way and like this is 5 right there. Okay, hits the y-axis at 5 and that point's open, but then this other one picks up right where this one leaves off at 1. If you put 1 for x, you get 5 for y, so that includes this point. And then from there, it's a line, and it's going to just go up with a slope of 4. Okay? All right. So it looks something like that. We need some points, though. It's like, say we go over to 4. Like, just because that's one of the numbers given in my limits of integration. Right, so what's that, 17? So this point, this is not to scale, I understand. I just put this here to show you. So that point is 4 for x, 17 for y. All right, so we're looking at the definite integral from 0 to 4, f of x dx, where f of x, our curve, is this, all right? It's a horizontal line at 5, and then a line of slope 4 connected to it. All right, connected at 1. So the meaning of this is the area contained like so. Okay, all right, tell me this area. If you can tell me how big this is, if you can measure how much space is right there, that's the answer to this, right? Well, okay, so sure, that's what it means. That's how we've understood it with the other problems. Maybe this graph is a little bit different. And you could do this lots of different ways. Let's do this. Let's see. I see right here now I'm going to break this into shapes I'm familiar with. Okay. I see a rectangle and a triangle. Okay. This rectangle is 4 by 5, right? The width is 4. The height is 5. All right, so my area in that shaded region, partially from the rectangle, is 4 times 5. Okay, So that is from that rectangle. Plus, what about the triangle? All right, so how wide is it there? Well, so where was this point? That point's at 1, and this point's at 4. So that has a width of 3. Okay, and then how tall was it? Well, so this point's at 17, and that point's at 5. So the width or the height is going to be 12. So right here, this part of it, that's 12. So that's 3 by 12. Okay. All right, 3 by 12. Now, all right, sure. We can break it down that way. I wanted to break it down into shapes I know about that are simple. Rectangle, triangle. Okay, so let's see. For the triangle, that's going to be 1/2 base, which is 3, height, which is 12. Okay, so I've got the whole thing now, given that I broke it down into a rectangle and a triangle. All right, so let's do the math then. Figure out what that's going to be. So this is 20, okay? And this is, so let's see, 6, 18, so 38. All right, so 38 square units of area. That's also the answer to our definite integral. So this is equal to 38, and I'll put the answer right there. I wanted to put it over here so you associate it with this, okay? All right, so there you see it, right? There are two things happening here. One, you have a way to think about what the integral means, okay? And I give you the area interpretation for now. And two, you have to know some basic geometric formulas, be able to sketch a graph, and you get some of the important points on there. But, you know, from there, the two of those things come together, all right? Okay, now let's talk about one more thing. This is somewhat obligatory, but I said that here's the notation. We call that the definite integral. We call A and B the limits of integration. There's a certain way that we read it. And I said as far as what it is or how you can think about it or how you can calculate it, there's this complex answer and then the simple answer. We focused on the simple answer in seeing that the integral can be thought of as area in one way or another. What about the complex answer? Okay, so it would be wrong if I didn't say a little bit about that. This is not something that somebody can just explain to you. It's going to take some reading and thinking on your own, okay? More so than everything else. But we're just saying that the definite integral is the limit as the norm of the partition goes to 0. So do you remember in the other video with Riemann sums, I would give you a curve and a partition and sample points, and here's the curve and the partition and the sample points give me rectangles in a certain arrangement. And if I find the grand total area of those rectangles, I get, you know, an estimation of the area under the curve, okay? But think about if we did that, but the widest rectangle in the partition went to 0. What would that look like? Well, I'll go back to my first video. It would be like this to this to this. Isn't it true that the more rectangles I fit inside the region, the more accurately they'll cover it? That's true, okay? So this is like saying that we'll find the Riemann sum as the widest rectangle there goes to 0. That means there will be more of them. That means they'll fit better. So that's why I can give my area interpretation of this. That's why I can say that the way that you can think about the definite integral is in terms of the area on the graph. Because it's defined in terms of the Riemann sum. But it's just like that this is the exact area. If the norm of the partition goes to 0, if these rectangles get thinner and thinner and there's more and more of them, they'll cover this with more and more accuracy until it's perfect, okay? That's what a limit is, all right? Okay, so, yeah, you can think about there's the region, say you got some curve, it looks like that. Here there's 3 rectangles, here there's more. That just trying to say as the norm of the partition, the widest rectangle gets smaller and smaller. The rectangles become more numerous. And as you keep up that process, chopping it up finer and finer, well, then eventually you have it. You got the perfect measurement of the area, and that's what the definite integral gives us. Okay, so the last thing I want you to see then is that it does take us to either of these interpretations. If you think of it this way, when you evaluate these in general,